Welcome everyone to the final session today of the Docker track. Today we have Dan Finneran speaking to us on Docker storage and designing a platform for persistent data.
Cool. So thank you very much for that welcome. Thank you very much for being here today for this session all around designing a platform for persistent data. My name is Dan Finneran, or as some of the colleagues that I have from Riley pronounce it Dan, and I've been part of Docker for around a year now. I'm a solutions architect based in EMEA, so I get to go and work with customers, get to help them deploy things, and generally get to learn from them, help them basically do better things with the platform. So why this particular topic? Why did I opt for storage when I was thinking about what I would like to present to people at DockerCon? As I mentioned, I do spend a lot of time working with customers. I go on site quite a lot and I speak to them, we look at their architecture, and there are common patterns that we tend to see, mistakes that can be made, and better ways of doing things. So really a lot of this talk and things that we're going to cover are things that I've learned whilst working with customers, best practices for doing things, better ways of architecting your application in order to make use of persistent storage so that you can scale out your applications, you can have them resilient and all of those sorts of benefits. This is the agenda that we're going to cover. We're going to look at immutability and how that applies to containers compared to traditional operating systems and ways of working. We'll look at the types of applications that have persistent data requirements. We'll look at how you can then use Docker to have that persistent data passed into containers, scale things out. We'll discuss Docker volume plugins, the benefits that you get from using them. Then we'll look at orchestrating storage. So we're going to use both Swarm and Kubernetes to scale out an application making use of persistent storage. There'll be a live demonstration of doing that, fingers crossed, towards the end. Finally, there'll be some key takeaways, a conclusion, and then hopefully time for some questions. So, immutability. This is kind of one of the core tenets of the best practices of containers. And really, the dictionary definition of it here, the container, the image once built shouldn't really change. You should really think of a container as being an engine. You put fuel into it, and you get something out of it at the back of it. So essentially, data comes in, is processed, and data comes out of it. Nothing should really persist inside a container itself. The container should be immutable. And when we talk about operating systems and containers, the older way of working, typically that you would see with an operating system, is that things would live inside the operating system. You build it, you deploy your operating system, you deploy your applications, you have some storage attached to that operating system, and things basically all live in that environment. That leaves you with very kind of tight coupling. You don't want your operating system to break. You patch it, you look after it, and all of those sorts of things. Whereas with a container and the immutable best practices and the key tenets behind that, there should only be the components that you require inside that container. It's designed predominantly to be automated, and it's not really designed to have lots of data inside it. As I say, things should go into a container, be processed by what's in there, and then the results pushed possibly somewhere else to another part of the service, to the stack, and all of those sorts of things. And in the event that a change is required, you don't go into a container and add new bits into it. We rebuild that container. Those are sorts of the best practices and key tenets between the two. So the core areas of an image, as it were. Images are built from layers. I'm sure most of you are aware of these kind of core concepts, but we'll quickly go over them. So when you are building your image, you typically start with your base, your first layer. Then you apply what you need to be on top of all of there, so typically your packages, the application that you have, and then any additional assets or additional libraries or additional code that are required. Once you've put your layers together, you have your new image, and that is what you will be running from moving forward. So, running an image, what does that actually look like? Well, when you actually run your image, you will pull that image if it's not already available. And then you will get a layer that sits on top of your image. And this is the copy on write layer, where anything that you write inside that container will persist whilst that container is running. However, once the process that's running inside that container has exited, that copy on write layer, if you've specified it, will actually appear. So going back, running your image again, you'll find that anything that you thought you had written inside that image has now disappeared because your copy on write layer is a brand new one as you've run that image again. So a lot of people kind of get confused when they first start using Docker. They get an image that they want to run, they run that image, they start applying things and making changes to it. They exit the image and think, job well done. They run the image again, and everything that they'd done on that copy on write layer has gone because it only persists for the lifetime of the container whilst running. So we're going to go over the sorts of application types that you will see that have those persistent data requirements. Quickly, what is persistent data? Persistent data is data that should be there regardless of the lifespan of the container. So containers can spin into life for seconds, minutes, hours, and then they can be gone again. Persistent data should always be there regardless of that lifespan of the container. And another thing to be aware of with persistent data is that regardless of where the container is ran or where it's scheduled to be ran, that persistent data should be accessible on any of the nodes in the cluster that's actually running. So that shared data across all of the nodes that make up your container platform. So when we talk about persistent data, we need to think about the ways that we access that persistent data as well. There are a number of different ways of connecting to third-party data. So you may have block storage. Typically, that will be attached as a disk to the node that's actually running. You will look at using protocols like iSCSI or Fiber Channel, and this is typically more of a one-to-one mapping. NFS, which is file-based storage, typically you will find that's many nodes connected to one NFS store, and the example that I'll be running later on will kind of go through and use NFS as part of the example. And then newer applications that are written, typically, any data that they process that needs to be persistent, they will use APIs to push that into a new image store, something that's based like S3 or something that uses REST-based storage. These are kind of the three main areas that we tend to see when people are putting their applications into containers that need to access persistent data. So this comes up quite a lot, and I'm going to try and put this to rest. Is it wrong to run a database inside a container? Now, one of the things about a database is that it requires persistent storage. There is no point having a database that as soon as the container is finished running, the data will just evaporate with the lifespan of that container. Now, a quick Google of that particular question, and you'll find quite a lot of responses that people have written about whether it is a good idea or is a bad idea to run databases in a container. So, is it wrong to run a database in a container? No. There is nothing wrong with running a database in a container as long as it's done correctly and as long as the database has the persistent storage that provides the capabilities that are required for it. And you don't need to take just my word for that. A quick look on the Docker store, and you will find that a lot of major vendors have started to push their databases into packages, into images that users can actually make use of. So things like Oracle DB, MySQL, MS SQL, and things like that. But what are the requirements of a database? So do it properly. You need to ensure that a database has persistent storage that has these requirements. So things like the correct latency, the ability for the amount of IOPS for speed and being able to do those multiple processes, and security as well. So some businesses may require that the data that is used in that database is in a secure area, so probably on an external file store that's in a secure area completely. So there are a number of requirements that are needed that you will typically see around databases. However, there is no reason why the database engine cannot run inside a container as long as it has access to a permanent data store that provides the functionality that is required for that database to run. Other examples of applications that require persistent data, batch processing is a very big one that we tend to see. So A good example is things like image processing. There'll be a large data store that has multiple images. When customers want to get one of those images, a container will spin up. It will take that image and do things like watermarking, or it will resize that image on the fly and give you the resized image that you're after. Other examples are format conversion. So everything would be stored in a raw format on a data store or a persistent data store. When you need access to it in a persistent format, a container will spin up, it will read that from a persistent data store, it will make changes to it, and you will get the format that you've asked for. And another example is transcoding. So some of the streaming providers, they have all of the raw footage that they have that's all high quality and things such as that. When you get a connection on your mobile device, a new container will appear, that's what you'll be connected to. It will take that raw stream and convert it into a format that actually makes sense for your mobile device that you're connecting from. And then finally, batch processing. So things like financial institutions, they have edge areas, so banks located in far-flung areas. They will essentially collect all of the data. At the end of the day, they will send all of that data to a central area, and then a number of processes will spin up, and they will all need access to that permanent data store to take all of that, process it, and then turn it into the format that they're after and give the results and do all of the batch processing that you would expect in a financial institution. And then another example are applications that just require persistent data between restarts. So a large number of applications park some data temporarily to disk under a number of circumstances, such as waiting for other areas of the system to respond and be ready to have data processed and passed to that next area of the stack through the application. Or alternatively, the data comes out of order, so it can only be processed once all of it is actually there. Or alternatively, bits of data sets that are just too large to be mapped to memory. So some of it will be cold parked to disk until it's ready or until there's a requirement to actually access it. So there are a number of common bad practices that we tend to see with people using containers in a wrong way, and this can lead to a number of negative results. Writing and storing your logs inside a running container is an absolute no-no. There is no reason to do it. You shouldn't do it at all. The reason behind that, if your application is running and continuously writing data inside the container, what will happen is eventually you will fill up the file system underlying where that container is running. And at that point, once that's full, any container that you try and spawn next won't have any additional space to spawn that new copy on write layer that we talked about earlier, at which point you've pretty much done a denial of service on your own host because you can't start any more containers. So the best practices around logs, push them externally. Have logs written to standard out and standard error, have the Docker engine take those logs then and push them somewhere else that they can be read. In the event the container crashes for whatever reason, you will have lost those logs because they were written inside the container in that copy on write layer, which disappeared after the container. So you have no idea why the container stopped working. If you push your logs externally, you can go get them, you can retrieve those logs, and you can do fault analysis on what happened to the container, the application inside the container. Another one is packaging large amounts of data inside your images. It becomes very slow to do the deployments. The smallest change, so if you have tons of images, assets inside a container, you change one image, you need to rebuild that entire container, and you need to pull very large parts of it if it's not already fully downloaded on your platform. So it becomes very slow, very tedious to do updates, to distribute your images as your platform scales out. So ideally, containers that all need to access the same sorts of data, they should do that through shared storage. So those are some of the kind of key bad practices that we tend to see with people using data inside of containers. We're now going to look at persistent data with Docker. So what do you actually do? What kind of things should you expect? And what does it actually look like? There are kind of three main implementations. One is per container storage. So when you run a container, you get some storage for the lifespan of that container. Shared storage, so that's multiple containers on the same host that are all accessing the same Docker volume underneath. And then multi-host shared storage. And multi-host or multi-node is important if you want to have scale-out capabilities. So as you add more nodes into your cluster, and you need an application that needs to access those volumes, it needs to be able to access it over the network or over whatever connectivity is available. So running your first container, as I mentioned, this happened to me. I think it's happened to quite a few people. You get Docker, you do a Docker run, something or other, you install everything, you exit that container, and all that work you did has disappeared with the lifespan of that container. What actually happened? So this is essentially the file path that you will see inside a host that is running the Docker engine. All data that is created after you run an image all lives inside that volume directory inside var lib docker. So you do a Docker run of your container, and when that container starts up, it's given a unique ID, and that unique ID is mapped to a new volume that's created inside the host itself. Anything that you write inside of that container will be immediately reflected on the host itself. And again, when this container exits, the processes inside it finish, those volumes will automatically be cleaned up and tidied up because they were only there for the lifespan of the container that was running. So that was per container storage. Now we're going to look at creating a volume and having a number of containers all make use of it. So in this example, we do a Docker volume create. By default, a Docker volume create will create a local volume. That means it will create a volume that's local to the node where you ran the command. So I've done a Docker volume create, and you can see under the volumes directory that that volume has now been created. To make use of that, when I do a Docker run command, I pass the -v for volume, I pass the name of it, which is dockercon, and I pass the path that I would like it to be exposed to inside the running container. So in this example, I've got /mount inside the container, and then the container that I'm going to run. So what does that actually look like? That's what it looks like. You can see there, the container is running. There is a mount folder inside the container, and that is actually linked to that volume that I've created on the host itself. If I start on another container with exactly the same volume being mapped, both of them now will be sharing that same underlying volume. The reasons why you would do this on the same host, so one application will be taking data from one particular source, it will be reading through that data, it will be writing changes to that local volume, and then the next container may be watching that directory, watching that volume. Any changes that it notices, it will take those files and it will process them and push them elsewhere. Alternatively, some applications that are hard-coded to write logs to the file system, you could have another container that sits there and ensures that those logs are taken, processed, and pushed externally. So that's shared storage on a single host. To really do proper clustering, to do proper scaling, we really need to look at multiple host clustering, multiple host shared storage, and persistence of data across a number of hosts. In this example, we have some shared storage through an NFS server, and then we have two hosts that are both running the Docker engine. So the first thing I'm going to do on the first host is create a new volume. With this, I've specified some additional options. In this case, the type of storage is NFS, so Network File System. I've passed it the address so it knows where to go to access that storage, the device that I'm going to access, so what the share is from that NFS storage, and then the name of the volume that will be created inside of the Docker engine. So one thing to be aware of here is that volume has now been created. However, it hasn't actually mounted the storage to the node itself. All it has done is updated the engine so that it knows that that volume that's been created maps back to that storage. And that's quite important. The reason being is if it immediately mounted as soon as you created the storage, you would have connections throughout your entire data center or in the cloud, wherever you have your persistent storage. And that becomes a bit of a security risk. It can also lead to connection troubles or a number of issues. So we run the same Docker volume create on the second host. Both of them are now aware they both have an NFS volume that maps back to this shared storage. Again, if I was to do the Docker run command, pass in the volume mount to that NFS volume that I've created. Again, we're going to mount it in /mount. So that's what you will see. Only when the container is actually running does the connection actually establish between the node that is running the container and the shared storage. And again, if I was to run the same command on the other host, any changes that I write inside that mount directory will instantly be reflected on the other container that's actually running as well. So for example, in this case, I could have a number of containers that are all running a web caching layer or some level of Nginx. On the shared storage, I have all of the assets, so numerous images, numerous web pages. I can scale out that container layer very quickly because I can use very small images. The assets don't need to be in that image. They can all make use of that shared storage. And it becomes very easy for me to scale outwards as I need additional load, as I need additional compute capacity to do all of the processing that's required on everything that's on that shared storage. As I mentioned, as part of the cleanup, when that container has finished running, so the process inside that container has exited, the Docker engine will take care of tidying up the copy on write layer. It will get rid of all of the config around that container itself. And it will immediately then get rid of that connection back to that external storage. So for security reasons, you don't have lingering connections. And for just general lifecycle purposes, it will tidy up after itself. So that was an example with NFS. There are a number of plugins or a number of capabilities that are built into the engine. However, there are a lot of storage vendors that have very clever technologies that they have that make use of, that you can make use of. So fast storage, encryption, tiered storage, and all of those sorts of things. In order to make use of those, we've extended the Docker engine to have capabilities for Docker volume plugins. For networking, this is the same sort of capability as well. So this allows us to extend functionality of the Docker engine itself. We already have an API, which means that it's very easy for vendors to use that API for them to write a Docker volume plugin, which allows the Docker engine to speak natively to whatever storage product it is that they actually have. It allows the user then to consume any existing storage and to make use of that functionality. And again, the way that the API works means that the same lifecycle will exist through that plugin. So when the container that is using that storage on that third-party vendor device, when the application has ended, that full lifecycle will take care as well. So there will be a full breakdown of the connection and tidy up afterwards. We have quite a few plugins in the Docker store. So if you were to go to store.docker.com, you'll find a number of these vendor plugins that have all been written by the vendors themselves. So things like HPE 3PAR and NetApp, etc., StorageOS, VMware, Dell Rexray. All of these allow you to take their plugins, install them inside the Docker engine, and start consuming their particular storage and start using functionality that they expose as well. It's very straightforward to use their plugins. So it's just a Docker plugin install, name of the driver that they've actually created. In this example, I have a company called Storage Driver, original, and my driver name is Array. Once I've installed that plugin, I just do a Docker volume create. I pass the name of the driver, any additional options. So this particular vendor has SSD storage available, and I can use that. I can ask for that particular fast tier storage, and I can also ring fence set capacity of it as well. So in this example, I've just grabbed 32 gig of SSD storage. It's created me a new volume, and I can now consume that volume in the same way that I did in the previous examples. So what's actually happening under the covers when you actually do a Docker volume create with a third-party vendor in most circumstances? From your host, the plugin will do API calls back to whatever it is that is sharing that storage. So it could be a disk array, it could be some cloud-based storage. That API call is then met with either a creating of a volume or just allowing access to that storage. And then when I do that Docker run, only then is that volume mounted or accessed by the node and mapped inside my running container. So in this example, I'm now consuming external storage through code that has been written by those vendors. There's a number of benefits and use cases for all of this sort of thing. So data-intensive applications. These vendors, these storage vendors, write very clever products that will allow you specialized tooling, specialized functionality that you can consume for data-intensive workloads. They also provide migration capabilities. So, for instance, being able to send snapshots off-site or move data from one area to another for DR purposes. They can make it very easy for you to take that data and reattach it elsewhere, so you get very quick application failover. And then there's also reduced mean time between failures as well. So we're going to look at orchestrating storage with Docker EE 2.0. The examples that we used earlier were one container. We did shared storage between multiple containers. We then manually went to each node that we were using, created a volume, and then used that volume as part of our example. That doesn't scale, though. In order for us to scale, we need to be able to orchestrate those particular steps. And with things like Docker Swarm and Kubernetes, it becomes very easy for you to have that volume described as a swarm volume, and then have services, containers as part of a service, consume that volume, making it very easy for you to scale across all the nodes that are in your cluster. So it's pretty straightforward. It looks quite a lot like it did when we did the Docker volume create. As part of your compose file, you will define a volume in there. So in this example, I've given it the same volume name, so it's called volume NFS. And then I pass in the driver options as part of that. So we're using NFS, so that's the type of a volume that we're going to be accessing, the address of the node that is going to be exposing that NFS, and then a number of options that will be needed to access that. So is it read-write? Do we want to have lock files and things such as that? So once we've defined that volume as part of our compose file, to actually consume it as part of the Swarm service, we create that service. We say which image we're going to run, and then we attach a volume to that image. And again, we say what the source is. So in this, the source is NFS, which was defined previously. The target is where it will be mounted inside the running container, and then any additional configuration as well. So that's what it looks like. That's how simple it is to define a scalable service that all makes use of persistent storage over things like NFS or other shared storage. So with Kubernetes, there are a few more things that need to be considered. There are a few more kind of specs that make up Kubernetes that you need to kind of understand in order to make use of it. The first is persistent volumes. And a persistent volume as part of the Kubernetes storage spec essentially is a volume that you make the cluster aware of. So you define a persistent volume, you give it the information of where that volume actually is, what it looks like, and the Kubernetes is then aware of it. However, to actually make use of that persistent volume, you need to make a claim. So then we have persistent volume claims. A claim is a request from a user, and that request can have a number of specifics. So the volume size that I want, the access methods, so whether it should be read-only, whether it should be read-write, whether that should be read-write or read-only across multiple containers or multiple hosts as well. And a persistent volume claim, when made, will make use of any persistent volume that's actually been added to the Kubernetes cluster. And then finally, we have a persistent volume. We have a claim against that volume. We then have the pod. Inside the pod is the container or containers that we're going to run. And then we have the volume mapping and the persistent volume claim, which maps it all together. So the pod is aware of the claim, and the claim has claimed the persistent volume and mapped it inside our running pod. So that's what it all kind of looks like. We're going to now do a live demonstration of both running a service on both Swarm and Kubernetes and consuming shared storage underneath. So fingers crossed this all goes well. So we have running here Docker Enterprise Edition 2.0. Sorry, 1 second. It's a 3-node cluster. Currently, it's not aware of any storage. There are no containers that are actually running on it. So the first thing that we're going to do, which would you like first, Kubernetes or Swarm? Swarm? OK. Sorry. I'll do Kubernetes in a second, but so, that went well. I didn't eat a fortune cookie, that's a good point. Sorry about this, 1 second. OK, let's try that one again. So as I showed in the previous example, this is the compose file that is going to define our service that we're going to run. We can see the volume. I don't know if you can see that OK. Let me just make it a little bit bigger. So down at the bottom, we have the volume that we're going to make use of across all of the nodes in the cluster. In this volume, we've defined where our storage actually lives, some options about it. And then our actual service, so we're going to run our DockerCon application. We're going to expose it. So the DockerCon application will listen on port 443, so it's HTTPS. We're going to map that externally to port 8443. And then we're going to use a volume inside that container, inside that service as well. So here we can see we're mapping our NFS, our shared storage, inside our running service. So quite simply, we will deploy this. So I'll create a new stack. So we're going to deploy this as a Swarm service. And we're going to call it application. So what's actually happening now is it's going to create a new overlay network because this is a service that's actually running. And it's actually going to create that service as well. So if we exit out of this in a second. So as we can see here, here is a service that's been created. We asked for 4 replicas. So it's running 4 of those containers that we asked for. And we can also see, if we look at the volumes, on each of the nodes, so the 3 nodes that are part of this cluster, is that app NFS volume. So that's been created on all of the nodes that's actually running our service. We can go to that service. So I've got a quick link to it here. So we can see, I'm not a very good web designer, as you can tell. But essentially what we have here is we have a number of assets that are all being accessed from the same underlying storage. So we can quickly speak to our apps team. So what we're actually going to do, we're going to publish some code and some assets to that NFS store. And now when we go back to it, we can now start to see that it becomes very easy for you to scale things up and have everything all being used from underlying storage. So every time I refresh, I will essentially be load balanced across the 4 replicas that I actually have. Those replicas then will all make use of accessing shared storage underneath. From this example, you can see the marketing team have spent quite a lot of time taking selfies over the last few days. That's not really what I wanted for the DockerCon gallery. So what I'm going to do, quite quickly, so what I've actually done without actually making any changes to the running containers, so again, back to the point around immutability, all I've done is change the data that sits underneath all of those 4 running containers. And now when I refresh, I get the DockerCon gallery that I was actually after. So Those containers can carry on running. Those containers are immutable. Nothing lives inside those running containers. They will just process what's actually living on that shared storage that sits underneath. So it becomes very easy for you to scale up, scale down, make changes from a data layer that can be reflected by the application layer that sits on top. So now Kubernetes. So we're actually going to run a swarm service that does the same sort of thing in Kubernetes, and we'll have them sit side by side. So what I'm going to do is I'm going to define our persistent volume. So we go to the Kubernetes area and storage. We've put in here, this is the YAML that actually makes up a persistent volume. Again, it's pretty comparable with the YAML that we used as part of our compose file. We have an NFS section in here which has the details of that shared storage. We will create this persistent volume. So that's now created, but Kubernetes hasn't actually done anything. It's just aware of that persistent volume and the capabilities of it. The next thing is to make a claim against that persistent volume. So the claim that we're going to make is essentially asking for a persistent volume that provides us with the capabilities that we can actually make use of. So when we actually do a claim, we can now see that they're bound in the status column. And what that means is that Kubernetes has taken that claim, looked at the persistent volumes that are actually available, and it has found that this persistent volume can be used, and it has bound that claim to the persistent volume that we created before. Now, the final step is the pods that I'm going to deploy. So I'm going to deploy a replica set, which is going to be it's going to look kind of the same as we did before. So this replica set has 4 replicas. It's going to run the same container in pods, and it's also going to have the volume claim as well here. So we've asked to do that persistent volume claim of the NFS volume that we created earlier, and we're going to map that inside the containers in the same place. And finally, we're going to define a service. So the service is essentially going to expose the pods that we're actually running and allow us to access what's actually running inside those pods. Okay, so we'll go to create here. Let's do this in the default namespace. So we've created a service. So the service is the front end that we will connect to, and it's also created that replica set as well. So in a few seconds, we will have those replicas that we asked for. So we'll have 4 pods that are actually running across our infrastructure, and the service that sits on top of all of those. If I go back to my web browser, wherever I left it, there we go. So I've got rid of that window. We're going to open a quick connection now to the Kubernetes address. Once it's come up. Uh-oh. There we go. So it took a few seconds to come up, but what I've actually hit here is the service endpoint of Kubernetes. It's running those 4 replicas, so we have my application that's actually running, and we're using that persistent volume claim to map down to the same storage. So we have swarm services that are running 4 replicas of the application, mapping to a swarm volume. And then we have 4 pods that are running. They've got persistent volume claims against the same volume that we're actually using as well. So at the moment, what we have is we have the same application managed by 2 different orchestrators, all consuming the same storage and all accessing the same data and providing the same capabilities as well. So with that, the key takeaways. Shared storage provides you with smaller images. If everything is going to be repetitive, repeated, then have everything accessing shared storage. It gives you much smaller images. It's much more efficient use of repeated data as part of your application. And it decouples your application and the data itself. So as you make changes to that shared storage, your containers stay immutable. You don't need to make changes to them. And finally, running a database is fine in a container as long as you've matched the requirements of that database that's actually running. And finally, don't write logs inside a container if you can help it. So with that, thank you very much. And does anybody have any questions? Cool. Thank you.